Hello, everyone, and welcome to today's live broadcast, Particle Size Distribution of Cement Using Laser Diffraction. My name is Sing Pham from LabRoots, and I'll be your moderator for today's event. We're delighted to bring you this educational web seminar presented by LabRoots and sponsored by Beckman Coulter. Beckman Coulter serves a diverse range of customers in the industrial market in areas such as aerospace, automobile, agriculture, chemicals, construction, fuels, electronics, just to name a few. Beckman is a key supplier to quality control and standard operating processes with a range of products in air and liquid particle counting, as well as laser diffraction for particle size distribution. We have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many questions as we can. You can enlarge the slide window by clicking on the screen icon in the lower right-hand corner of the slide window. If you have any technical problems viewing or hearing this presentation, please click on the support button at the top right of your presentation window or submit your problem through the green Q&A button lower left. I would like now to introduce today's speaker, Edward Hoff. Edward Hoff is a graduate of the University of Miami with a BS in chemistry. He is a 43-year veteran of Coulter Corporation and Beckman Coulter in the Particle Characterization Division. Ed started his career as a chemist in the Applications Lab, eventually transitioning into product development and marketing manager roles. He has helped develop the Multisizer series, LS series for laser diffraction, and the N4 dynamic light scattering system, just to name a few. In recent years, Ed moved into field sales and is now a sales specialist. With 43 years in the particle characterization industry, Ed has a wealth of application knowledge across numerous markets. I will now turn it over to Ed for his presentation.
Thank you, Sue. Today, as Sue mentioned, we'll be discussing particle sizing of cement using laser diffraction type instrumentation. And the areas that we'll be discussing will be the importance of particle size analysis for cement, the use of laser diffraction, also the LS13320, which is Beckman Coulter's laser diffraction system, and the importance of how this is transitioned in the marketplace. We'll be discussing flexibility of modules, that is, how to present samples to the instrumentation, and also quality data, comparing to ISO standards as well as NIST 114 SRM's 114Q for cement. So traditionally, methods used in the cement industry have been Blaine number, Wagner turbidity meter, and probably more commonly SIDS. But these only provide a single number or limited size information about the cements. And what has happened over the years as cement requirements have, high-performance cements have been needed with more stringent requirements, the particle size distribution information is needed in more detail to more properly control the quality of the cement and versus its performance, desired performance. The complete size distribution has been increasingly important, and so over the last 20 years or so, technology advances have been moving toward the laser diffraction type instrumentation for a variety of reasons that we'll get to in a moment. But one thing you want to consider is that not all laser diffraction particle size analyzers are created equal. They may be based on laser diffraction, but how you implement and design everything from sample handling to optics will contribute to the quality of the results you get. This is just an example of some distributions that are can be quite complicated. Usually distributions are not Gaussian or very symmetrical. They could have multiple peaks because you're typically dealing with blends of materials that might be being measured. And one of the key things you want to consider in a instrumentation is that you can analyze these without prior knowledge of what the distribution shape is. And so that's a consideration to consider when you are looking at diffraction type instruments. Now, if your particle sizes are too large, you have an abnormal amount of large particles present, you can get crumbling of your cement, like in the left photographs. And if they're too small, too many fines, you can get cracking of your cement, especially with temperature changes or pressure or stress on the cement. So these are things you want to try to optimize. And the only way to properly do this is to have really a detailed particle size distribution than trying to figure this out from instrumentation or prior devices that would only give single numbers or limited number of channels like in sieves. Now, the advantages of laser diffraction is multi-folded. These instruments are quite easy to use. They cover a broad dynamic range. In other words, from submicron particles to usually multiple millimeters, so a couple of thousand microns down to below a micron. They can do this quite fast. Typically, results can be in 1 to 3 minutes, thereabouts. Could be a little longer depending on if running liquid systems. The other advantage is these type of instruments are quite reproducible and also operator independent in the results. These kinds of instrumentation can be run in a dry state or a liquid suspension, such as alcohols or hexane or some other solvent that might be desired to run. So particle systems can be dispersed in that or run in a totally dry state. And as mentioned above, very important is the operator independent results. The instrument doesn't care usually what type of who's putting the sample in, as long as it's a representative sample. That's really the key for any particle size analysis. Brief discussion on ISO standards. ISO standard 13320 discusses some key factors that are important for laser diffraction that one wants to consider in their design. ISO took these into consideration. So resolution and sensitivity of the result. In other words, you want to be able to resolve different sizes easily and be also able to sense small changes in a particle system. If the distribution is changing, be able to see these readily. Reproducibility, of course, is very important. And then accuracy of the results. And we'll discuss these in more detail later in the lecture. The LS13320, of course, the name LS13320 comes from the chapter number for ISO standard, mainly because this was the first instrument to truly follow the full standard, the ISO standard, and that's where it was named from, LS standing for light scatter. And there's two types of models in the optical bench we'll get into in a moment in detail, but basically you have what's called a multi-wavelength optical bench, which allows if you're running with liquid-based samples, can cover 17 nanometers to 2,000 microns in a single scan. And then there's the single wavelength optical bench. It has less optics in it. does not have the bottom end optics. And so you're covering 0.375 microns to 2,000 microns. Two ideal modules that we offer that would be ideal for cement if one was going to want to run in liquid-based systems, where you can, typically liquid systems, you can control dispersion a little bit more, but that may not be how the powder is being utilized. It may be utilized in the dry state, but we have the universal liquid module, and then also for doing in a dry state, totally dry state, the Tornado dry powder system, and we'll discuss these in details in a moment. So some key features of the LS and that one wants to consider, and these are, of course, benefits for the cement applications. I mentioned earlier about not wanting to, for complex distributions, not wanting to have to input information about distribution shape. We usually don't know this prior to analyzing the sample. So we have essentially what's called automodality, we call it, where there's no requirement for operator input into distribution shape. You don't need to know is it bimodal, monomodal, narrow, broad, multi-peaked. You don't have to know anything about the sample distribution shape to get the proper, correct answer. Secondly, on resolution and sensitivity, the LS series has what's we call a unique binocular optics. So it has allows us to pick up a wide range of light scatter, wide angular range that is, and we detect this wide angular range using a 126 detector diode array, and this is very important for giving us that resolution and sensitivity to detect very subtle changes in distributions that one might have if the process changes, because you want to know when things change quickly, so you can make adjustments in your process to keep the desired particle size. On the other side, accuracy and precision, it's controlled by the angular position, or knowing the angles of light scatter. You basically know two things about your particle size distribution. You know the angle, and you know the amount of light that's being scattered due to your particle size distribution. From that information, the particle size distribution is a calculation, converting that light scatter, utilizing either Fraunhofer or Mee theory to get the appropriate and accurate particle size distribution. And positioning and aligning of that system is extremely important. And we have this, I'll show a picture of it later, an X-pattern low angle detector that allows us to position and hold about a 1 micron tolerance on positioning that laser beam. And this gets us the very accurate and very precise results, so we can get good precision as well as very accurate results. And then lastly, ease of operation. Most of these systems have built-in, or you can create SOPs or standard operating procedures, and essentially allow a one-button operation for your particle size analysis. So these instruments can be used by production people. They're not very complicated to use, so the results are analyzed quite fast utilizing this mode, and in systems will either automatically clean themselves if it's a wet system, or be ready for the next analysis in a short amount of time. with very minimal contact with the computer. Also available on the LS is for those that want to correlate back to screen sizes or mesh units. There's a SID stack correlation you can use when you want to, if you desire this capability. And so we can individually correlate to individual screen sizes, and you would select the screens that you use, and you can correlate the results so the LS can give out the same type of correlation. Because usually, laser diffraction instruments measure more of the volume of the particle, so when you're sieving, you're measuring the middle dimension of a particle. So you can correlate back to this size. You can apply a correlation factor in the instrument's output to correlate directly to screens that you use. Briefly, this is a layout of the optics. In this area here, we have the binocular optics, and then our low-angle detector, which I'll show a picture of in detail a little bit later. The upper section of the instrument is what we call PIDS optics. I'm not going to go into details of what PIDS is all about at during this lecture, but suffice to say this allows for the low-end measurement below a half a micron, 0.4 of a micron, and down to 17 nanometers. For very accurate measurement and very high resolution measurements down in that region. Another sort of unique feature of this coiled area here is essentially a spatial filter, but it's a fiber optic cable. It's a patented design of Beckman Coulter's, and this essentially eliminates the need for about 20 pinholes in lenses and things that can obviously go out of adjustment from older design systems. And utilizing this fiber optic cable allows a very clean signal to be, because what you're trying to create is a very clean signal from the laser and a very stable signal. And so this allows for great help in being able to, if one is needed, to actually put a new laser in a system in the field without any problem. Briefly, the two modules that I mentioned, the universal liquid module is our for running any kind of fluid. It can handle any Class D solvent. Holds approximately 120, 125 mils of fluid, and this is circulated by a centrifugal custom designed pump designed specifically for particles, handling particles. It can work with aqueous fluids as well, but obviously in cement you're going to be running solvents if you're going to be running in the wet state. Depending on which optical bench one has, you can go as either 17 nanometers to 2000 or 0.375 to 2000, depending on which bench you have. This module will rinse itself between runs. It can auto-dilute in case you've added too much sample. We want to keep a certain range of obscuration so we can get light through the sample as they pass the laser. It has built-in sonication. This is an optional item if one wants it. And it can also fill from a built-in pump, so it can fill from a container automatically. On the dry side, the amount of sample one uses is based primarily on the size distribution. You typically like to add enough powder to run about 20 to 30 seconds. This should give you a very good representative sample. So that would typically be your run time. And no matter which bench you have, the size range running dry is going to be 0.375 microns to 2,000 microns. And it uses vacuum only. We use like a vacuum cleaner, high-quality vacuum cleaner we offer that's well-grounded, so you don't have any static forces or anything like that. And I'll get into its unique design, why it's called Tornado, in a moment. But this module is designed to disperse the powders very well and essentially be ready to operate. There's no cleanup when you run dry because all the powder is passed through and gone to vacuum. So you're essentially ready for your next analysis immediately. The universal liquid module is pictured next to my slides here, and essentially in the center section there is where you would put your sample. You're only needing to put in a small amount of sample. These can be pre-dispersed outside the instrument, or you can add directly a dry powder or a suspension already directly to the module. So if you want to prepare the sample in the module, you can do that. Since it has built-in sonication, you can control the power and the sonication time and so forth appropriate to the material you're going to be analyzing and what might be part of an SOP. This would all be controlled by the computer. You're continually keeping the particles suspended, so you have a homogeneous mixture, and these are going through the passing the laser beam, so we can definitely multiple times, so we can definitely get a good picture of what the distribution, light scatter intensity distribution looks like, so we can then calculate the appropriate particle size. Most people are tending to start going to the dry powder systems because of its ease of operation. There is no sample prep. You're taking the powder directly, or get a representative sample, and you're placing it in a what looks like a small graduated cylinder, and placing that in the sample module. This goes into the same orientation as the liquid module, fits into the same slot. And effectively, the dispersion is going to be controlled by the vacuum and the flow path, and also how the dispersion takes place, and I'll show you some schematics in that in a moment. But one key thing about this dry powder system is that it analyzes all the powder that you give it. That's what dictates how long the instrument's going to run. So you might add, depending on the distribution, a half a gram to maybe a couple of grams, again, depending on the size distribution. The bigger the particles are, the more volume of powder you might have to run in a short period of time. But you're typically going to add about enough material to run 20 to 30 seconds. But by analyzing all the powder, you eliminate any subsampling error, any segregation that could have taken place. Once it's on an instrument, it doesn't matter because the instrument's going to analyze all the powder that you gave it. This is a little closer view of the material, of the module, and the sample chamber is right here, where you're going to place the sample in a cuvette. And it has a vortex type action. And this is a patented design that we created back a number of years ago. And this design, we took into consideration the possible use of pressure and vacuum, and we worked out this unique system where it only required a vacuum, like from a vacuum cleaner type device, and the computer controls the exact vacuum that you put on the system, but you can typically are going to run with about 12 inches of water vacuum for most applications. And basically, in detail of how it works is you have an up and down platform that the sample module is positioned on. This platform rises and lowers. You have a fixed position suction probe, and then as the platform rises, the powder starts swirling around, and I'll have another picture in a moment, a little closer of the vortex nature that's taking place. But the powder gets pulled up, flows through and down through a measuring cell. This is a laminar flow cell that keeps the particle stream in a nice tight stream with laminar flow that's flowing through it to keep that particle system stream. So it keeps your, actually it keeps the particles in a close stream, so you don't have a lot of spray. So there's essentially your windows and things like that in this closed chamber essentially don't get dirty very often. So maybe once a year they have to be wiped down depending on the excuse me, type of powders that you're going to be dealing with. And then out to vacuum. And another little closer up, what happens is we create vortices right above the surface of the particles as the platform rises and particles start going through. The instrument, the computer, controls that platform that I mentioned because it wants to control the feed rate. Excuse me. Wants to control the feed rate so we have a constant flow of particles in front of the beam. And also these vortexes are like little mini tornadoes, so it creates a very high shear area, and so you have high shear but low velocity, so you tend to disperse the powders very well, and then of course the low velocity, we don't want them banging around or hitting any hard right angles or anything like that. So for cement, it's not quite as fragile, but some applications you could have fragile particles that might break if you have too much velocity. And this can happen in pressurized systems where you are forcing the particles under very high pressure. You can tend to break them. But this is a more gentle way of dispersing the particles and have them flow through the instrument. And once the system is analyzed, everything in the container, that container platform, everything goes down to the bottom of the starting position, and you remove the cell. And essentially, you're ready for the next sample. So we'll discuss here and show some data here in a moment for resolution, sensitivity, how it affects reproducibility and accuracy. So we'll be showing some data and some additional slides here. Also the results here on 114Q. So resolution and sensitivity is very important. It's controlled by the geometry, the number, the position, and geometry of the detector elements I mentioned earlier. We have a 126 detector diode array, and what you need to really define is this raw intensity data as pictured in the graph. And because what you get is pictured in the right there, you'll get some pattern depending on the distribution of your particles. This pattern can vary, and the intensity of these rings and dark spots can vary. And so the better you can define this distribution of your light scatter pattern, the more accurate the results can be. Also the resolution, and be able to determine is it bimodal, monomodal, have 3 or 4 peaks or a little side peak. that might be not visible with some systems. We can make these measurements because of the high number of detectors and the fact that we read these detectors simultaneously for the same particles. So we can make a very accurate measurement here. Because as I said earlier, you know two things: light intensity as a function of angle. So the better you position these things and measure these things, the more accurate and precise your data is going to be. This is a schematic drawing of the low-angle detector array, and it forms what we call an X pattern with the beam dump right in the center. So right in the center you have your beam dump, and that's where you're aligning the laser to, because that fixes the position. And as I said earlier too, you might have angles as low as or under 0.02 degrees and out to as far as 145. But when you're dealing with particles with, say, 50 microns and above, these low-angle detectors are extremely important, and the ability to align that laser is very important. Also, the sample handling of always flowing representative powder, or if it's in a liquid system, keeping the particles suspended and homogeneous throughout the measurement is extremely important, as well as the optics. But this allows us to very easily position the laser beam, and when one does this, it takes a few seconds to do an alignment on the instrument. The instrument will automatically do this periodically, so the operator doesn't have to remember when to do it. But this will ensure very accurate, very precise results from both the instrument to instrument. So if you're comparing one plant to another, you should be getting the same results. And also within the same instruments, precision and accuracy is improved by this basic design. In discussing accuracy, and I'll show some results in a moment, of course, accuracy is defined as the closeness of a result to a true accepted value. So you're going to be running controls or standards that, and I'll show one in a moment, but in the ISO standard, this is defined as being able to measure the D50, the median mean size, and be able to get 3 measurements, and the deviation should be less than 3%, which is pretty generous by our standards, but from the certified value. And some results that are displayed here is a Duke standard. This one's about 1 micron, just shown as an example, and looking at the results. And this has a 0.3%, so it's 10 times better than what's required by the ISO standard, as an example. And then last but not least, when analyzing real cement, utilizing the NIST SRM 114Q, the NIST values for the standard are the diamond-shaped positions, with the blue lines being, you have to be within, and now this standard's for laser diffraction instruments, and one has to be within the blue lines for to be acceptable. And so what we did here is run both the Tornado, the dry module, and the universal liquid module, and we in the dry module is the dotted or the dash red line, and the universal liquid module is the smaller blue dots. And you can see they're well within the error bars of the standard itself. And so this shows quite good agreement between both wet and dry. So as long as you can, and cement typically disperses pretty well, both in a wet and dry state. So when things are, there's no problem with dispersion or stickiness of materials, wet and dry should agree with each other similarly like this. And this shows the quality of data you can expect from the LS for running cements. And that's pretty much my talk. I'll be available for questions here in a moment. If you have additional questions that come up, you think about things later, I've got an email address for Dave Dunham. He'll be glad to take questions, and we'll get answers back to you. Also, for those that might be attending the World of Concrete in Las Vegas this coming week, we will have a booth there. N871 is our booth number. We'll be there and be glad to answer any technical questions. Also, we'll have a live LS, so if you have any samples, we'll be glad to run 1 or 2 samples for you and get your results. And I thank you very much.
Well, thank you, Ed, very much for that informative presentation. Before we get started on the question and answer session, I would like to remind our audience of how to submit questions. You can submit questions by typing them in the Q&A box, which can be found by clicking on the green Q&A button at the lower left of the presentation window. We'll try to answer as many as we can. Now, while the questions are coming in, we would like to conduct a poll asking how likely are you to recommend this webinar to a colleague. Please respond with your answer on a scale of 1 to 5, with 1 being not likely at all and 5 being extremely likely. Okay, and our first question is, can you bring one of these systems to my location for demonstration?
Yes, we can. Most all the sales reps in particle characterization have a demo unit, and they can that can certainly be arranged to come in and do a demonstration at your plant site. Also available, if you wish, is you can submit samples to our applications lab, and we're glad to run them in our lab and get you the results right back. And this is at a no charge, of course, for lab samples, and of course we'll be glad to show you the LS in doing a sample at your site.
That's great. Our next question, Miguel asks, what is the life of the sensor?
Typically, lasers, these are solid state lasers, so they can run, depending on its use, if you're operational 24 hours a day, or let's say you're operational 24 hours a day, you're probably talking 8 to 10 years. And if you're going to be running just 1 or 2 shifts, that could be somewhat a little bit longer. I usually don't see or hear about lasers being replaced maybe 12 years out, 14 years out. So
that's great.
They last a long time.
That's great. And you mentioned the lab analysis. One viewer asked, how do you submit a free lab analysis?
That can be done through our website. You can go to particle characterization and access it through there for submitting particles. You can call up and discuss your need with your local salesperson, particle characterization sales rep, and he can give you the exact details for submitting a sample. Up to 4 samples are run at no charge, and and so that can be arranged. A lot of your communication will be all done through the web, as far as downloading the application form for the lab, and then it gives you details of where to send it and so forth. They're either going to be run in our Miami lab, where these instruments are manufactured, or our Grants Pass, Oregon lab, for those that might be on the West Coast, a little closer. So those are two locations for our laboratories.
That's great, all those resources. Another person asked, how many samples can I run in a day?
If you're running dry, that's going to be the quickest way, since you're not having to rinse the module. Your typical analysis time might be between a minute to a minute and a half per sample. So you can run in an hour. You could run 40 samples in an hour running dry. If you're constantly ready, you have samples available and ready to feed. You can fill up these little cups. You get 10 cups with the instrument, and you can just constantly feed, and the data is automatically being saved, so it's as fast as almost as fast as that you can feed samples to it and tell it to operate. So it's not difficult to do a very high number in a day, an 8-hour day. So you're probably talking in the area max out about 30 to 40 samples, 45 samples an hour.
Wow, that's great. We have a lot of people who are interested in the lab analysis, so Beckman Coulter will send out a sample analysis link as a follow-up to this webinar, and you might be able to see this link as it pops up right now. Okay, so if we have no more questions, then I would like to pass the control back to Ed and see if he has any last comments for the audience.
I wish to thank everybody for attending, and for those that are going to be in Las Vegas next week, I will be there, so look forward to meeting you. And as I said, we'll have several technical people there, so be glad to answer additional questions that might come up. And please don't hesitate to email Dave Dunham if you think of some questions later, or talk to some associates and questions come up later. I'd be glad to follow up answering them. And thank you all very much.
Well, I'm sorry, I see some more questions coming in, and since we have some more time, let's go through them. So another person asked, how does the auto rinse work?
The auto rinse is computer controlled. The module has a high level, top level sensor, optical level sensor. So we drain and fill the module 3 times, or this is actually selectable by the operator. Cement rinses pretty easily in cement components. So typically you would need no more than about 3 rinses of your module, in other words, a fill and drain. And the computer controls this speed of filling and draining, and this operation takes about a minute and a half between samples to actually rinse the module and then fill it with clean fluid, so you're ready to add another sample and run another sample. But it's quite automatic, and as I mentioned during the lecture, the universal liquid module has a built-in pump, so it's drawing fluid from a source. So this can be a container, a 5-gallon container, or a gallon bottle of sitting on the next to the instrument or underneath the instrument if it's a 5-gallon container. it can draw it up from the floor. So it has a very good diaphragm type pump to pull clean fluid up for rinsing purposes. And then it's going to go into a drain container. Since this is a solvent, you don't want to dump it down the drain. And that drain container also has level sensors, so when it gets full, it will stop the ability to keep adding fluid to it, so you don't have any overflow. And it's time to drain the rinse container, or the waste container. And that comes with the instrument, the module.
Okay, that's great. We have another viewer who asks, could the tornado overcome the effects of trace amounts of liquid in the dry powder samples of having particles stick together, such as oil or water vapor?
Part of that's going to be dictated by the how much water vapor we might have. And what I mean by that is obviously you'd like it dry, but definitely a few percent moisture can be present, and it can disperse that. It's one of those things you'd probably want to try and compare it to running it in a wet state. Wet state, you have more control over your dispersion. You can sonicate, you can wet, so you can add chemical dispersants. Usually not so much require chemical dispersants when you're running in solvents. But the dry can overcome quite a bit, but it's a kind of thing you'd have to test to see what the upper limit, especially if it's an oil contaminate. I think you mentioned oil contamination. That's going to be a little more stickier than something that might be dry. But it does overcome moisture, but there are limits, and it's the kind of thing that you'd want to test. But if you're doing dry sieving, if you're doing sieving already, then the tornado can do the same, can do those kinds of samples. If you're not having a problem doing sieving, the tornado is not going to have a problem.
That's great. Well, once again, I would like to thank Ed so much for his presentation. That was very informative, and we had some great questions. Today's webcast will be available for on-demand viewing through July of 2016. You will receive an email from LabRoots alerting you when this webcast will be available for replay, and we invite you to forward that announcement to your colleagues who may have missed today's live event. See you next time, and bye, everyone.
Bye.